Okay, welcome to the talk. If you're coming in, please close the door behind you. Please give a warm applause to Magnus. He's going to talk about high-dimensional 4D geometry and fractals, which is used in electric sheep and for other exciting pictures.
All right, hello everyone. As you may have seen in the abstract, this talk will be split into 3 distinct sections. The thing about the topic is that it's extremely wide. I could probably fill a lecture for the whole week, but we're not going to do that. So I am going to assume you roughly know how to do perspective projections in 3D. If you don't, you might as well believe me. That would be good too. So for the 4D part, I'm gonna throw some formulas in there how to do that. Then I'm gonna talk about some iterative function systems and how they generally work. And in particular, after that, I'm going to talk about fractal flames, which are a special kind of iterative function system. So the twist we're going to do here is that for the iterative function system and for the fractal flames, we're going to talk about how to do those in 4D. Now, and when I say 4D and higher dimensional, I mean R to the power of 4 and higher. So it's not about higher dimensional stuff as you would have it in other fields of maths. It's more condensed into something specific. All right, and there's going to be some intermission slides where I showcase some demo program. I got like the cheesiest URL possible, so you can follow that along in your browser if you feel like it. And let's get started. So when I said when I have 3 parts, I am going to tell you what I'm skipping. So this is a cube. We've all seen a cube. The stuff I'm skipping because we don't have enough time is how to do vector matrix and matrix products, which is like the basis for most of the linear algebra stuff you've heard of. I'm going to skip the cross product in 3D. I'm going to assume you roughly know what homogeneous coordinates are. If you don't, it's basically you add another coordinate and you have a scale. I'm going to assume you trust me on rotations. You basically need, in 3D, you need a 3x3 matrix to have a rotation. The reason for homogeneous coordinates are that we want to have some affine transformations, which is basically the same, but we can also like translate stuff. There's lookout transformations in OpenGL. So also skipping those, but we're going to extend them later. And there's something called the perspective transform, which is basically what we saw on the slide before, which it reduces the number of dimensions. So in the 3D case, you get a 2D picture, which you can plot on your screen. And well, yeah, so the perspective transform is something you do so you can later do projections. There's going to be a lot of slides like this. So for example, since I'm going to skip over it, but I'm going to point out an annotation, like vectors in our stuff are going to be bold. Vertical bars around the matrix mean that we're going to do a determinant. And when we have rotation matrices, we can just extend them to be, so you can multiply them with affine transformation matrices. So you just add another row, and you add another column, all zeros except for the last cell. So it's going to be interchangeable. So just a heads up. And this is a matrix we're also skipping. I'm just throwing that here because it looks kind of intimidating. It's documented in your OpenGL manual, so yeah. Just throwing it out there. Okay. And my clicker's not working. Anyway, so now part 1. You guys are going to believe me that we can do perspective projections in 3D, probably because you've been playing Call of Duty or something at some point. So we can do that in 4D, and this, for example, would be a tesseract or a hypercube. So in order to render this, we need to do some maths to take our 4D object, in this case a tesseract, and reduce it to a 3D object, which we can then turn into a 2D object. And if we want to do it in 5D, it's going to be the same thing. So again, what do we need for that? It's basically the same list. Shit. But it gets worse because we don't actually have a cross product in 4D. Damn it. Well, we don't need a cross product, we just need normals. And so I'm just going to do a difference, which is a lot shorter. Okay, so we want to do normals. I was just showing him a slide for the cross product, and it's pretty much the same thing. But like in 3D, we had a cross product, and we take two vectors, and we get an orthogonal vector to that. So this is the property we need to do our predictions. Now, in 4D, we can't have two vectors and multiply them in some way to get something orthogonal, because then we get a plane, because we didn't fix three of the vectors, so we have one left over. But we can take three vectors and do a determinant with this matrix here, and that'll do it. So this gives us one of two vectors, just like the normal cross product. So we just solved the normal / cross product problem. So yeah. And of course, we need another base vector, because usually we just needed three of them. So I call this term because we all like quantum physics. Anyway. We can also do this in higher dimensions. It basically looks the same, except so what we do is, if we have anything in n, we need one less than that, and then we can fix all the other coordinates, and then we get a vector back that's going to be orthogonal to that. So, which is part of the formulas we need later. I'm not gonna go into the whole formulas most of the time. You can just read up on them later. I'm just gonna throw the version out that I use for the stuff. So another thing we need is a look-at transformation. So in 3D, I mean, you have a point you're looking at, and you have your camera. So you need to turn around and face that point. Fortunately, we don't actually need trigonometric functions, because we can just build a rotation matrix by filling in the last column of a matrix with what we're looking at minus where we're from. And then we need some orientation vectors. In 4D, we need two orientation vectors. If you're looking at your OpenGL manual, you have a function that does that for you. You give it three vectors. You give it where you're looking at, where you're looking from, and which side is up. So because you could rotate the camera like this. So in 4D, you need to fix another vector for that. So we have two from up and back, and we fill from right to left. We calculated the last column, and we do our normal or cross product over those vectors, and then we go to the left, and we slide out one of the vectors, and then we keep doing that, and the last one, we have another normal for everything. Now, you can actually find this in some publications online, but you can't find this, which is what we do when we want to do it in like 5D and stuff. It still looks the same, but it's ugly. But basically, we have two less in the number of dimensions, and then we slide the calculated columns in from the right and calculate towards the left. Right. So we also want to do a perspective transformation, which is what basically you have a camera like this instead of like this, so it goes like to the sides. So that's part of the perspective thing. Fortunately, since OpenGL is actually taking care of all the cutoffs and everything, and we really just want a 3D object, we can skip a lot of stuff, and the matrix doesn't look nearly as ugly as the 3D case. So we can use a simple matrix like this. What we want to do is we only have our eye angle, which is like how wide our eye can look, and everything but the last two dimensions, the last one dimension, and this is the homogeneous part, they're fixed with the eye angle. So the last coordinate in our 4D, 5D, whatever, is always kind of like a death. So yeah, so basically that works. The 5D case is pretty much trivial. We just have the last two fixed, and whatever we have is corrected with the eye angle formula we had in the 3D case. So that takes care of that. And then we need some kind of view matrix, which is basically like we take all of this stuff, put it all together, and then we're happy because we only have one matrix that we have to multiply with for our vector. And it's not that bad, it's just a couple matrix multiplications. This is actually a 4x4 matrix, and this is a 5x5, and this is a 5x5. But that's not so bad, because we can just, so we implicitly expand this one to 5x5 with, as I previously explained. So not too bad. And the 5D is pretty much the same, so we don't really have to worry about this. So I mean 5D and higher. So, what do we do once we did our matrix, vector matrix multiplication? So we still need to actually convert, so we gave it a homogeneous 4D coordinate and our matrix, and we multiply those. And then we get still a 5D coordinate back. And at this point, we need to take the homogeneous part out, and we also need to do a perspective division. So this is the same function in both cases, so we just apply that twice, and then we get a 3D vector back. And that's basically it. So now we have a 3D vector, we do the 3D thing again, we have cameras for every dimension, and we're going. So, yeah. And now to show how that is done, or at least what it looks like. So this is the IBQ from earlier. And we can rotate this in 3D, nothing too fancy. It's a little program I wrote a while back. And we can do it in 4D. So, and then it turns inside out. Yay, it turns inside out. If we did this with a 3D thing in 4D, we would basically turn the whole thing inside out, because we do a 4D rotation on a 3D object. And we can also do this in 5D. And it gets kind of confusing after 5D. It's so we stop at 4. Saner. All right. Okay. Now, I promised some iterative function systems. We're going to have to skip over a couple of these things, so it's not too bad. So an iterative function system, the basic idea is that you have like 2, 3, 4 functions, and you have a set of starting vectors. So you multiply all of these with all of them, and then you do that recursively, and there's a function like this, and you sum it all up. And this is actually from a Fractal Flame paper. I don't quite agree with it, because we don't really do that ad infinitum when we display it, because then we wouldn't see anything, because it wouldn't ever stop. So that, yeah. But that's what the Fractal Flame paper had. So we can basically choose any kind of function we want for this. A simple one is our affine transformations, which are basically we can like take our point, we can translate it, and we can rotate it. So normally you do a chaos game to render these things, which is explained later, but I'm not going to do that because we can't. It doesn't work in 4D or 3D because you need too many points. So what we can do is we take a sufficiently divided primitive and then apply all of these functions recursively, and then we get pretty pictures. So for example, if we try to do a Sierpinski gasket, we have this square. And then we have 3 functions, and they work like this, where they realign it and they make it smaller, which we can all do with affine transformations. We do that a couple of times recursively, and we get an ever nicer and ever sharper picture. So does this work in 3D enough? Sure. We can do that. There's no problem here. I'm going to stick with a 3D one. These are randomly generated just with a seed, so just so you know. So nothing too fancy here. We can rotate this. It kind of looks pretty. We can do this in 4D and turn it inside out. And so you can turn it inside out, as you see here, sort of. Iterative function systems in 2D, but they use a special kind of function called a variation, which is defined in that Fractal Flame paper by Scott Graves, which is referenced in the end, so you can read it, because it's cool. And the variations kind of work like this. You have your affine transformation, and you also apply a set of variation functions, which are defined in appendix. There's like 49 canonical ones. They kind of look like this. So, for example, we can have a function that does nothing. We can have a function that applies signs to all of the coordinates. And also like a normal spherical transform, all sorts of kind of funky things. There's a couple of weird constants, and they thought about some cool stuff there. So what you do is you take a number of these variations, and then you blend them together by assigning weights for each of the variations you want, and adding it all together. So you can have like half of a spherical one, a quarter of a linear one, and another quarter of a cosine one. You can also make it more than one, but then it kind of looks weird. So then they also added post transforms, which is you take another one of these and do it again, and a final one. Yeah, they really like their transforms. They do it everywhere, which is kind of cool. So when I said the things about the chaos game earlier, so if you only do the chaos game as normally described, you get a black and white picture. Some pixels are hit, some aren't. That's not really pretty. You can improve that by counting the number of times you hit a particular pixel, and you have a grayscale image, which is better. It's a lot better if you take the logarithm to do that, because you have lots of spots that get hit a lot of times, you have lots of randomness in there, so you want to smooth out some of these smaller things, some small differences, but you still want to show like some of the bigger ones, so logarithmic scale kind of worked for them. And if you apply a column map, the way they do that is like every function you have, because you still have more than one function, every function gets an index on a column map, and you mix them all together. And then you get much prettier pictures, and then you add some vibrancy algorithm. It's always good. Now, as I said, this algorithm is strictly in 2D. So it looks 3D, but it's not. So can we do that in 3D? Well, we can't do it with a chaos game because we don't have enough memory for that. But we can do it. We can do it with a discrete version. So, yeah, I spent some fun time on this program. So, let's hope it doesn't crash. Okay. So, we want more precision. We want this to be bigger. This already kind of looks cool. It's already in 4D. So let's stick with a 3D case for now. You still get the effect of it turning inside out and everything. So this is kind of a random one, just the first best seed I had. You notice that it's 2D because I just took a plane and subdivided it a lot of times. And when you run the transforms, you can sort of extend some of them, like you've seen the cosine one, and you can just add a number cosine. You've seen the spherical one, you have a formula for spheres in higher dimensions, so all is well. And we can do that. We can do that in 4D also, which means our stuff can turn inside out. But the cool part about the fractal flame algorithm is actually the way the colors work, which turns out is really easy to implement in a pixel shader if you're willing to do logarithm in a pixel shader. It sounds worse than it is. It actually works pretty well in real time. So this is rendered in real time. It's not the prettiest set ever, but there's some room for improvement here. So, and it's kind of nice to see that it's still pretty damn smooth. So I can do some random colors. Okay, let's take this one. So like the yellow and the purple and the blue, which is sort of visible, they're all different functions and they get mixed together in the pixel shader, which works surprisingly well. And we can do all sorts of pretty ones. The previous one is actually pretty nice because it highlights some of the properties. Oh yeah, this one is pretty good. So depending on from where we look, our pixel shader with the original algorithm has this kind of property of amplifying geometry, which is pretty cool. And we can, again, do this in any kind of dimension we want. So we have this cool thing. And we can make it turn inside out. Whoa, sorta. Right. So you get this nebula, and by doing a 4D inside-out thing, you can make some pretty amazing pictures if you find where I kind of see and everything. So this thing, this piece of code, is all open source. It's all available on GitHub. You can play with it. It runs in your browser. Although, unfortunately, it turns out that WebGL doesn't seem to support floating point textures. We just need to count ones up, but unfortunately, variables are clamped, so it doesn't really work, which is kind of sad. But it still works in principle, and you can play it with most of the other things. So yeah. That's a program if you're interested. There's a blog series explaining most of the formulas in more detail because 30 minutes just wouldn't cut it. This is my Twitter, if you're interested. Here's the original paper about the fractal flame algorithm by Scott Race and Eric Recasset, which is a really amazing read, and they put a lot of cool stuff in there, so I always give it a read. And as I said, some of my explanations were from French. We've all seen the LSD one. And that's the end of that one, so if anyone has any questions.
Okay, thank you, Magnum, for this really interesting talk. I really liked fractals. I'm sure everybody here does as well. Before we start with questions, if you absolutely have to leave, please be quiet. That involves no talking. If you can, please just stay until the end of questions. So, are there any questions from the internet, Signal Angel? Can you wave at me if you have any questions? Is there a question? Yes? Okay, ask away. Audio Angel, or so, could you please turn on the Signal Angel's microphone? Let's start with a question from microphone number 3 until the Signal Angel is set up.
Okay, Hi, thank you for your interesting talk. I was wondering, in the projection transformation that you explained, you assume that the last dimension, it's 1, so it's going to be depth, and yes. Then you assume that the rest are going to collapse. My question is, what happens if you don't assume that, or if there is anything that changes? Because in the projection, you're kind of assuming how the projection is done to 3D, right? If I understood it correctly.
That is true. I haven't actually explored what happens if we do a different kind of 3D transform in this case. So. I mean
that perceptually it could be different.
It could be. I've just tried to take the perspective projection as used in OpenGL and extend it to 40 and 5D and higher. So I haven't explored if it gets different, but it would definitely be amazing to try that out. So I totally agree.
Yeah.
Okay, Signal Angel, do you have a microphone?
Yes, I have.
Okay, please ask away.
Standard user from IRC asks, are these visualization applicable to the 3D virtual reality experience, and will that give us the ability to better understand 4 and 5D fractals and projections?
I'm sure that if we have something, a virtual reality headset that can do things in 3D right in front of us, that would completely improve the experience, and it would definitely help us explore the higher dimensions better. So I haven't, again, tried it, but if someone would like to try that with VR gear, I'll be the first to test it.
Okay, let's go back to microphone number 3, please.
Yeah, just a quick question. I noticed that even for the multidimensional cases, you used apparently 2D primitives as the primitives wouldn't it be possible to use the high-dimensional primitives?
It would definitely be possible. So as you said, what I did was I still used tries. And I kind of cheated by basically making them see-through, as in, because if you had a 4D, if you're looking at a 3D object with 4D you can see all of the sides simultaneously. So it would definitely be possible to take higher dimensional primitives. It's just that it's a lot easier to reason about if you have something like a 2D primitive and you're trying to wrap your head around it.
Okay, are there any more questions from the Internet Signal Angel?
Yes, there is.
Okay, ask away.
Twiley Sparkle from IRC asks, do you think a game in 4D plus would be possible, and do you think it would be playable?
So there actually are games in 4D and higher. I remember at least a game called 4D Maze, and there's a couple of the adaptations of the Rubik's Cube to at least 4D, 5D, and I think I've seen 7D. With Rubik's Cube in particular, I have to admit that I can't solve a 3D one, so I would be amazed to see anyone solve a 4D one, but it's possible and it can be done. So actually, when I was thinking about doing this stuff, the transformations kind of look really cool, and it would be kind of cool to use it as like a transformation effect. Like you have your scene and you have another scene, and then you can do a 4D swap over them, which I think would be really cool. But I'm not sure, like, I would love to see more games like this. And there are some, but, yeah.
Okay, are there more internet questions?
Not so far.
Not so far. Okay. One more from microphone number 3.
Thank you for your talk. I have one question regarding using it not just with fractals like you did, but just inserting 4D or ND data sets from real data. And does it work, and how it would maybe look like, and what trick you used to get the transparency effect for this data set?
So, I mean, in the demo, I basically just used a transparent 2D surface. So that part was easy. But I could see this used in higher dimensions to visualize data sets. So, I mean, when you're looking at a lot of stuff where you analyze stuff into different categories, you always end up with more than 3. So if you were like to draw a graph, it would probably be very easy to make a planar one in higher dimensions. But I've not seen this done yet. I would love to see this done. But unfortunately, it is kind of hard to wrap your head around the 4D rotation part. So I'm not sure if, because the graphs are used to make stuff easier to see. So I'm not sure if it will make it easier to see if you're not trained to see 4D. But it would probably be cool.
Okay, we have time up for about 1 or 2 more questions. Let's try microphone number 2 for a change, please.
Hey, thank you for the talk. I have some sort of more theoretical question. I was wondering, you told us that there are 47 types of variations, and I never heard of variations. So what actually, do they have some sort of properties? It's kind of a very small class.
So they're just basically defined at the end of that particular paper with the HTTP URL here. This particular paper. So they're specifically defined. The only common property they really have is that they're sort of aesthetically pleasing on their own, and that they're all 2D. So you can extend some of them, you can't extend others. But they're specifically defined in the appendix of that paper.
Okay, thank you very much.
Okay, one last question.
Yes, not a question, just a quick info on the 4D games question. So there is a game that made the rounds on the internet this year called, and I have no clue where the word comes from, so I can't pronounce it, Megakure, M-I-E-G-A-K-U-R-E. You can look it up. And what you can do in that game is like, you have a 3D environment, you look at it in the 3D sense, and then like you get to a wall, and in your dimension that you're currently in, you can't walk around the wall, and then you can shift to the 4th dimension or into another version of your 3D world along the 4th axis, and then you can go around the wall. Right. And in gameplay terms, it's really just that you shift to another dimension. I mean, a lot of games do that. But the funny thing is that that game actually implements it with the correct math, so it looks really, really fancy.
I remember seeing that. I haven't tried it. I wanted to try it. So I mean, it makes sense that it works because when you do the 4D projection, you really end up with a 3D world. So it totally makes sense that you could use this to turn parts of the world around. So I've seen it. It looked very cool, but I haven't tried it. But probably will.
Let's thank the speaker again, please.